So last time we were looking at power functions, and I want to review that today, and then we'll look at circular motion. And I've booked some time in the HE study area where there's computers are with autograph on, so we can try and go down there and do some work on that hopefully, but we'll see how time goes. So laws of indices are something that we will use a lot, particularly when it comes to calculus. They're the sorts of things that we refer to when we're tidying up algebraic expressions, when we're doing power, playing around with power functions, stuff like that. We use these laws of indices. So I asked you to make a note of them somewhere convenient so you can refer to them. From those came these laws of logarithms. Reminder that logarithms are powers of 10. There's no base. This actually means the base 10. So that means I'm turning a number into a power of 10. What power have I got to make 3? What's the power of 10 to give me 3? That will be the logarithm of 3. And because I've turned them into powers, it means I can turn a multiplication into addition, division into subtraction, and most importantly, I can turn this power of n into a multiply. And so that's the one that we'll be using, or we did use last week when it came to playing around with these power functions. So what did we do? Well, we looked at some experiments, some results. And the suggestion is that these results have this form, p equals ri to the n. So p equals ri to the n of that form. We can prove it's of that form by plotting a graph of not power against current, but something else. And then if we get a straight line, we'll know we've got the right relationship. So what we did was we played around with this function and arrived at, using logarithms, this function here, which is the same as this. It's the same function, but written in a different way by using logarithms. And then we compared that with the equation of a line, y equals mx plus c, and saw that if we plot not power, but the log of power, against not current, but the log of current, we get a straight line, and the gradient of that line will give us the value for n in this function here, and the constant c, the y-intercept, will give us the logarithm of the value of r. So in that, from there we could find r, and that's the sort of thing we did last time, if you remember. A very useful and powerful technique. So instead of plotting power against current, we plotted log of power against log of current, and we found that we got a straight line, and then we found the gradient and the y-intercept using this equation of the line information. Then we looked at other types. Instead of x being in the base, which it was in the first one, hang on a minute, an oscillating speaker, headphone. So instead of x being in the base, x is in the exponent, we have what's called an exponential function. And so now we do a similar sort of thing. We take the log of both sides and play around with it. Now we notice that to get a straight line, instead of plotting so log y, instead of plotting y, we plot log y, but now we plot x, so we plot log y directly against x, and if we get a straight line this time, we'll know that we've got a function of this form, where x is in the power. And again, the gradient will allow us to find b, because it tells us the log of b, from which we can get the base, and the y-intercept will tell us the logarithm of a, so we can find out what a was. So again, you plot the line to allow you to find the values of the constants in this function. And then we said that in cases where the rate of change of the function depends on the value of the function, and a very common occurrence that is, for example, population growth, radioactive decay, charging, discharging the capacitor, anything where the rate of change of charge, for example, depends on how much charge there is on the capacitor, then the base number in this function here, this base number there, turns out to be the same value each time, and that's called the natural number e. So then we have these functions. They're probably the most important functions that you'll use, power functions. You've already probably come across them. And because this base turns up a lot, instead of using logarithms to the base 10, we use logarithms to the base e called the natural logarithm. So ln is the natural logarithm. And you've got a button on your calculator that allows you to find the natural logarithm of a number. So if we take the natural logarithm of both sides, we end up with this. And so instead of plotting y, we plot log of y. And instead of plotting plot x, we plot log y against x. And again, the gradient tells us k in the function, which is this value here. And c, the y-intercept allows us to find the value of a in this exponential function. So a very common way of finding out what these constants are, k and a, in an exponential function. Plot a graph of log, the natural log of y against x. When we go down to the HE study area, I'll be asking you to maybe, and we maybe started looking at these last week, I think. Chapter 30, there are some exercises in there you can have a go at playing around with those functions. It's just a case of getting used to using it. Okay?